Welcome back. Please welcome David, who is a software engineer at Google working on KUnit, a unit testing framework for the Linux kernel. And he'll be speaking to us today on kernel testing with KUnit, bridging the gap.
Thanks. Good afternoon, everyone. As you already know, I'm David Gao, and I am going to be talking about kernel testing with KUnit, bridging the gap. So, who am I? As mentioned, I'm David. I've been using Linux basically full-time since 2006, and have been working on the KUnit kernel testing framework at Google for the last 3 years. And in this talk, we're basically going to cover what, why, and how you should test the kernel, and particularly look at KUnit, which is what I work on, and kselftest, which is the other main in-tree kernel testing framework. In particular, we're going to cover what's been changing and what's improved, both in KUnit and in how it interacts with kselftest, and how, in general, these testing frameworks work over the last year, and where we're looking to go in the future. What we're not going to be talking about is actually a step-by-step guide on how to write tests with KUnit. There are lots of other talks about that out there, but this should provide a good overview of what KUnit is, and as a preview, we'll be bragging about how much better our documentation is, so there's plenty you can find out about that. So let's get started by talking about testing the kernel and why you should do it. And the reason you should test the kernel is quite obviously because you want the kernel to work. In fact, you really want the kernel to work, because security and reliability bugs are bad. In the kernel, they're really bad. The kernel has access to literally everything, and if it crashes, your entire system goes down. So there's a pretty good incentive not to break the kernel. Similarly, the kernel's been around for a long time, there have been a lot of bugs in it over time. We don't want to have a regression where a bug we thought was fixed came back. And automated testing, as has sort of been well described by most people in the software engineering field over the last several decades, is a really good way of doing that. So there's a little bit of history. Kernel testing's come quite a long way since Linus basically said, hey, if I can get the kernel to build, it's good, and if it then boots, it's perfect. These days, we have a lot of tools for testing the kernel, and these largely started as people working on some feature saying, hey, I can write a script, or I can write a test module once modules existed, and just execute some code, check the results, see if it makes any sense. The downside is lots of people writing their own tests in their own way ends up with something of a mess. There are lots of tests that, each do their own thing. So kselftest and later KUnit are both sort of attempts to standardize these tests. And they're both, as part of being standard, in tree. They're part of the Linux kernel source tree. You go to kernel.org, you download the kernel source, both KUnit and kselftest, and all of the KUnit and kselftest tests are there in the tarball you downloaded. As part of being standard, they're also automatically being run on a few different CI systems, and generally the community is running these as these are the tests that you run as a kernel developer. There are other kernel testing systems that are not sort of in kernel. These are also very useful, but we're going to focus on the in-kernel ones today. So I've mentioned kselftest and KUnit. And sort of the big question that no one's had a really easy answer to is, when should I use one and when should I use the other? So basically that's the question I want to start off by trying to answer. Kselftest is basically a bunch of scripts that run in user space. Each test is a script that exercises some kernel functionality just by executing whatever's accessible. So it might be, a syscall, it might be reading something from sysfs, it might be, say you wanted to test ext4 as a file system. With kselftest, the way you would do that would be have a test that mounts a file system image that you've got and does some checks on that from user space. You're getting sort of a whole view of the system, but not much view of exactly internally how it works. Kselftest is really convenient, but you can't access anything that is inside the kernel. Like, you can't just say, I want to call this kernel function directly, or I want to read the contents of this variable in my tests. If you want to do that, you need some kernel code. And there are some kselftest tests that have kernel modules that they build and run to expose these things. But the better way to handle that sort of thing, where you want to test individual kernel functions or individual kernel variables have the correct value, is to use KUnit. And KUnit is basically designed as a unit testing framework, so you're going to be testing like individual C functions within the kernel. And it has the advantage that all of the test code is part of the kernel. It's built into your vmlinux.so, your VM Linux file, or it can be loaded as a kernel module itself directly. You want to call a kernel function, you can just call it. This does make it a bit trickier to write those big integration tests that cover the whole journey from you run mount to the file has the contents you want. But it means if you want to test something like, the code that parses timestamps in the directory entry or something, you can have a test that tests just that function and passes all the possible inputs that, would be awkward to have in like a test file system and verifies them one by one. This means that things have to be written exactly in C like other kernel things, or I guess Rust in the future, or assembly if you really, really hate yourself. But it also means that, if you can use the kernel, it works. There are no extra dependencies. So that's really when you should use kselftest and KUnit. Are you trying to check sort of the external behavior of the system, or are you trying to check individual functions? There are some other testing tools that the kernel provides that are useful to know about, but don't actually do the same sort of thing. So there are a bunch of dynamic analysis tools, address sanitizers, concurrency sanitizers, memory leak checkers, etc. But these are, to some extent, orthogonal to KUnit and kselftest. Instead of testing that a particular bit of code works and gives the correct answer, they're just looking for common classes of failure. Like, memory corruption, accessing things you shouldn't, deadlocks, etc. This means that sort of the way I like to think about it is a test like KUnit and kselftest is something that can pass as well as fail, whereas these sanitizers, they're not testing a particular bit of code. They'll just run the entire length of time the kernel's running, and they might fail if something goes wrong, but you can never use them to say, this is passed, I know it's all good. Similarly, there are code coverage tools. I suspect everyone's got a pretty good idea what code coverage is. And as with many things, there are two different ones you can use with the kernel. Again, these are a useful tool to have alongside KUnit or kselftest tests. That's an awful lot of different information about sort of what tools there exist. So it's understandably confusing, and one of the things that we've done on the KUnit side in the last year is actually written all of this down and put it in the kernel documentation. So the first sort of great achievement of the last year is actually, this is written, there's now the kernel testing guide in the kernel documentation with a happy link there that goes through what all of these things are and when you should use each in a little bit more detail than we can squeeze into half an hour here, and has all of the appropriate links spread through. So if there's one thing you should learn from this talk, it's really, if you want to know how to test the kernel, there's now a document telling you how to do it. So we've got these two kernel testing systems in kselftest and KUnit, and trying to get people to use the right one for the right purpose, and there have been some challenges over the last year in doing that. And the first thing really is around integration. KUnit and kselftest are in a lot of ways very similar and serve very similar purposes, and the same people probably should be using both. We don't want to be in the situation where someone says, well, I like kselftest better, I'm going to use it for everything instead of KUnit, or vice versa, because they're different enough they don't want to need to learn how to use both. So one of our goals has been to basically bring these closer together in the areas where it doesn't really matter, where the differences don't count. So one of these is you want to be able to port a test from one to the other and get results in a similar format. You want the same CI systems and same pieces of tooling to be able to handle results from kselftest and KUnit the same way. The other thing is there were some feature gaps that KUnit, and in particular KUnit's tooling, has had compared to kselftest. And the main one here is that KUnit's tooling was entirely based around this thing called user mode Linux, or UML. And UML is basically a custom kernel architecture which compiles the entire kernel as a user mode normal x86 Linux executable, which is really neat and works really fast, so you can run your tests with KUnit extremely quickly, but totally lets you down if you want to test something that's architecture specific or that involves some sort of hardware that UML can't expose. And while UML is improving a lot in what sorts of hardware it can expose and emulate, this was really a gap between KUnit, particularly its tooling, and kselftest. So that's something else we wanted to address in the last year. So let's start with the first one and talk about KTAP. So when you have a bunch of tests, you need to output their results sometimes, whether they passed or failed. And before the days of kselftest and the like, this was done basically by people's scripts doing whatever the person who wrote the script thought made sense at the time. So some tests would print out all was well, some would return a particular error code, some would print out nothing on success and just error messages on failure. And unless you knew what that specific test script did, it'd be different from everything else. You'd have no clue. So it was agreed to standardize all of the test results with kselftest and other related testing tools on TAP. Now, TAP is the test anything protocol and is this very simple output format for test results that I think originally came from Perl or something. It's very simple. It's basically just a small header with TAP version whatever, a list of how many tests, and then a bunch of lines saying OK, test 1, test name, not OK, test 2, just OK or not OK for each test. And a couple of slightly more interesting things for a couple of other cases. But in general, extremely simple and worked pretty well. Doesn't upset anyone, it's human readable, except it's a bit too simple. kselftest and later KUnit both wanted to do things, and the big one is have nested tests, where you can have tests that have subtests. And so you can have a single result file with all of your tests that are nicely categorized. And TAP had no support whatsoever for having nested tests. So every test and every test system tried to hack nested tests into TAP in their own way. And we ended up basically back where we started. In KUnit's case, we found a draft version 14 of the TAP spec that had nested test support and implemented something that was almost but not quite that, and tried to convince everyone to use them, and it turns out nobody liked TAP 14, even the people who made it. It was abandoned at some point. The actual spec text was under a slightly weird license. It was not a great base to build off. So it was decided, and Tim Bird from Sony sort of really got the ball rolling here, that we should come up with our own specification based on TAP that would have everything that the kernel specifically needed in it. And there were some discussions around that last year and a bit the year before, what we'd do. And we picked it up again, particularly one of our interns at Google, Ray Moore, to finish off and write a new full specification for this output format, which rather than being something completely new, would rather basically just standardize what kselftest and KUnit tests are mostly already doing, and that tools mostly can already parse, and just shave off a few of the sharp edges. So we've got something that mostly works already and is a reasonably solid base to build off once those few things that need changing have been changed to match it. It also got rid of some unnecessary stuff, like nobody wanted embedded YAML or JSON in the kernel, even though the TAP spec technically supported it. So this is what a TAP KTAP output looks like. It's very basic. I'm not going to go into it in detail as we've all got better things to do, but it's basically you've got a header line, a plan line, and you can nest test results. So you've got an entire nested set of test results. In this case, there are 36 tests, which all have interesting list test names, and they all passed, and the bottom one also passed, which is the sort of aggregate of all of these. All the subtests passed, therefore the test as a whole passed. A more complicated example is this one, which has some tests which are skipped. We'll get to skip tests later, but you can mark tests as having been skipped. Tests that have failed, comments which are called these diagnostic lines, some statistics about how many subtests passed and failed, and because something failed, the whole thing failed. And this is reasonably nice and human readable, but KUnit already had a bunch of tooling for parsing its own variant of TAP. And we want to expand that so that it can be used in kselftest as well. And so there's this script. It's part of KUnit and therefore part of the kernel tree. Tools testing KUnit, KUnit.py, run the parse option, pass that in, and you get a nice prettily printed summary of the results. It'll print these diagnostic comments, but only for tests that have failed. It will give the statistics even if the test didn't print any statistic lines itself. It's pretty useful. We're really glad that kselftest will be able to use this in the future, and again that Ray Moore, who was our intern, rewrote all of the parser for this to make it robust against things kselftest did but KUnit didn't. The other big feature is QEMU support in KUnit tool. So KUnit itself, as I mentioned, works on all architectures the kernel supports. It's just more C kernel code. But this KUnit tool, which will automatically build the kernel for you and run it and parse the output and print those nice summaries, was specifically based on this user mode Linux architecture. So we've fixed that. KUnit tool now can cross-compile to other architectures. There's a cross-compile flag. You can just pass a GNU compiler triplet in, and that will let you pick a compiler. There's also an Arch option, which you pass an architecture in, and there are a bunch of pre-written configs that will cross-compile the kernel for you using that particular architecture, and then run it under QEMU, and extract the test results, parse them, print a nice summary. So that means basically you can create your tests and then, oh, I want to test these on S390, oh, I want to test these on x86, oh, I want to test these on a big Indian system, a PowerPC one or something, and it's possible very easily. At the moment, we support quite a few architectures, all of the really popular ones, I think. x86, ARM, Alpha, PowerPC, RISC-V, S390. There are actually some S390 specific KUnit tests. And it's quite easy to add new architectures. There's just a Python script containing a whole bunch of config options for it, the kconfig options, the arguments that need to be passed to QEMU, what all of the compiler names are by default, etc. And this, I can't understand how useful it is to be able to just quickly test on another architecture, and in particular a real one, rather than the UML sort of virtualized run as a user mode process one, which is fast, but does behave a little bit differently. There are also a bunch of other new features in KUnit that some are more related to TAP and some aren't. So since last year's LCA, there are a bunch of these new things. The first one is that we've got a release notes page that lists them. So if you've been following KUnit, you should definitely check in on that to see what's been introduced in what new versions. It still, I think, says 5.16 isn't out yet, as we need to update it, but it's got all of the actual features there. And those include tests can now be skipped. We talked about this last year. It exists now. It's actually upstream. You can use it. The test statistics stuff I pointed out, print statistics there even when you're not using KUnit tool. And there were a few people who had the need to print those sort of statistics out as a blocker for using KUnit instead of whatever custom script they'd done before. Integration with the underlying behavior sanitizer. The documentation, I've mentioned a couple of times, has been drastically improved in the last year. It's been totally reorganized. If you go into documentation, DevTools, KUnit in the kernel source, there's now a better architecture overview. It's structured a bit better. It should be much easier to get started with KUnit, and a bit easier to find specifics on how do I write tests versus how do I run them versus how do I use the KUnit tool wrapper or how do I do it manually. And bug and usability fixes. There are also a number of better ways of selecting which tests get run. If you're a maintainer, you can now put a .kunit config file in a directory of the kernel source code for your subsystem and list all of the options that you want KUnit to use when testing that subsystem, and people can pass the path to that KUnit config fragment in, the path to that subsystem in, and the kernel will be built with all of those features and tests included, and will be run. So that's a great way of saying, run with this, and you can execute things, see all of the test results. This is what I expect before you send me a patch. Similarly, if you just want to add one extra config option to one of these, there's this kconfig add option. Simple, I want to run the ext4 tests, but I want to enable kasan or something like that. It's very easy. Test filtering, you can filter what tests run at runtime as well as at compile time. And that lets you build your kernel once and run several different tests in several different environments with it, which can be quite convenient too, and is a prerequisite for hermetic testing. We all know that tests in theory should leave everything the way they found them, and it shouldn't matter what order you run the tests in, because test A is not going to break test B that runs afterwards by scribbling over memory or whatever, but equally in the real world that doesn't always happen. So to help debug those cases, there's a run isolated option to KUnit tool, which will run each test or each test suite in its own invocation of the kernel. So they can't stamp on each other's toes. Very useful for tracking down weird bugs where memory has been corrupted or the like. Finally, there are a bunch of new tests. This is always my favorite slide. In the last year, we've doubled the number of test suites in KUnit. In 5.11, we had 20. In 5.16, there are 40. From 204 individual tests to 324. And this is despite the fact that the parameterized test feature that was merged at the end of 2020 now has basically merged a bunch of other tests. So the number went down before it went up. But some of these new tests are really neat. One of them, I won't go through the whole list, but one of them I want to point out is these timestamp conversion tests for converting from Unix time to civil time. It turns out someone's written this paper of how you can use this frankly terrifying bit of algebra to do this really efficiently. And in order to introduce that to the kernel, they used test-driven development by writing KUnit tests for the existing naive implementation of the conversion, then implemented their new algorithm, and then checked that the test still passed. And that's really neat. They've done that for both regular timestamp conversions and RTC clock conversions. Kfence is a new memory checker. There's sound driver, SD card driver, Thunderbolt, multipath TCP, stack unwinding for the S390, memory management. Daimon's really cool. This was the first project that actually used KUnit, and it's finally upstream, so we're really excited. Basic kernel functions and C functions like memset, memcopy, memmove all actually have some KUnit tests. The hashing for files, it's all there. So what's coming up in the future? We're going to fix all of the things to actually match this new KTAP standard that we wrote. We've started on that, but there are still obviously a number of things that now we know what the standard is, we can bring up to it. Improved support for running KUnit tests as modules is a big one. As KUnit developers, we mostly build the tests into the kernel image rather than loading them as modules afterwards, but KUnit does support this. And Jeremy, who I think is here, has started proposing this new way of handling modules that is a lot less weirdly hacky than our old one. So we're looking forward to improving that. More test examples, particularly for testing hardware. We've reduced memory usage and stack size even further, which is particularly useful since Linus was whinging about it when W-error went in, and a number of bug fixes and documentation changes. The final thing is, please reach out if you have any questions for us. I'm very curious if people have actually been using KUnit or kselftest and if there's anything blocking people from doing so. Whether maintainers in particular want to have lists of tests they want people to run using this KUnit config mechanism or another, like an entry in maintainers saying, please run these before you send me patches. And do contributors like the idea of that? If you send a patch, will you tell people what you've tested in it? And how much refactoring of code, I think this is going to be the theme for the next year, is acceptable to make something more testable. Because a lot of code in the kernel is intertwined in a way that makes it difficult. Okay, questions, comments? I see there are a few questions here, so I'll get started. The first one from Andrew, TAP-wise, are we going to be okay with reporting multiple sets of results where kernel tests may be run at different times, like initialization versus device probe versus module init? This basically is one of the tricky things. KUnit's tooling, we're hoping to make handle, okay, if there are multiple sets of results, we'll be able to merge them. It's not quite done yet, but in theory, it should be able to work. Most tests, when you run KUnit, run it in it. And there's this debugfs way of getting the individual results for things that are loaded later. Do any CIs run kernel tests with random enabled config options? I know there are some that at least build them with random enabled config options. I'm not sure off the top of my head if any of them are running. There are some that run with... I think there are. There are certainly some that run with pretty large all yes config style setups. The hermetic testing... Can the hermetic testing run isolated feature be used for targeting specific drivers tests only? E.g. when developing an out-of-tree prototype driver against a stable kernel? At the moment, run isolated as a feature can't be used to separate one driver from the others in the same execution, but you can combine it or use instead the glob filter thing to run just a particular driver with a separate invocation of KUnit tool. So it's definitely possible to do that. You just, if the driver was called foo, you can just kunit.py run foo star, and it'll run all tests that start with foo. So if you name things well, it's easy.
Well, thank you very much, David. That brings us to the end of our time slot for this talk. and David will be more than happy to take further questions or comments outside of the session.
Yes.
So
Thank you.
Thank you very much. We'll now take another 10-minute break, and we'll be back at 5 p.m. for Russell Curry abusing GitHub Actions for building and testing kernels. See you all then.